Hey, Dr. O here, and I'd like to talk a little bit about buffers. Before we talk about buffers, let's make sure we have a good understanding of acids and bases. Acidic solutions are going to have high concentrations of hydrogen ions as well as a low pH number. And we could write an equation for hydrogen chloride, which is an acid, going into solution like this. So what's actually happening when hydrogen chloride goes into water? Well, let's bring up a vat of water and drop in some hydrogen chloride. Now, like any acid or base, it's going to dissociate into ions. And in this case, it'll be those acidic hydrogen ions as well as chloride. Now, water is considered to have a neutral pH, which means that the hydrogen ions and the hydroxide ions are going to be in balance. So we could think about the balance of water initially looking like this. But we just added a bunch of hydrogen ions by dropping in the hydrogen chloride. So now we've tipped the pH scale towards the acid side of things and created an acidic solution. So what about a basic solution? Well, they're going to have a low concentration of hydrogen ions, but a high pH number. And we could write an equation for a base, such as sodium hydroxide, going into solution like this. And what's actually happening in our vat of water? Well, like an acid, the base will form ions in water. In this case, sodium ions and hydroxide ions. So essentially, we have previously neutral water where our hydrogen ions and our hydroxide ions balanced, but we added some proton-accepting hydrogen ions and therefore made an alkaline solution. To review what we just stated, acidic solutions will have high hydrogen ion concentrations but low pH numbers. And we used hydrogen chloride as our example. And we also stated that a basic solution, an alkaline solution, will have low hydrogen ion concentrations but a high pH number. And we used sodium hydroxide as our example. And we further stated that neutral solutions, such as water, will have equal concentrations of hydrogen ions and hydroxide ions. So there's one more concept that we need to look at before we get to buffers. So let's do that. Some acids are considered strong acids, while others are considered weak. So how does a strong acid behave? Well, let's take a look at hydrochloric acid and drop it in some water. And we can see that it will dissociate into hydrogen ions and chloride. So we could say then that a strong acid dissociates completely in water. Then how does a weak acid behave? Well, carbonic acid is a weak acid, and if we drop it into water, we'll get some acid dissociating into ions, but some of those molecules will stay intact. So for a weak acid, we could say that weak acids don't dissociate completely in water, and therein lies the magic of weak acids. Now, bases can be strong or weak as well, and we can take a strong base such as sodium hydroxide and put it into water, and we could predict, based upon what we know now about strong acids, that it's going to dissociate completely in water. And on the other hand, we could take a weak base such as ammonium ion and predict that it won't dissociate completely in water. Now, some of it will dissociate into ions, but some of it's going to stay intact. And we can conclude for weak bases that these don't dissociate completely in water either. So now that we know about weak acids and weak bases and that there's some magic there, let's talk about buffers. So what is a buffer? Well, a buffer is a solution that can resist abrupt changes and large swings in pH. So how does it do that? Well, it does that by either binding hydrogen ions, if there should be a big influx of hydrogen ions by the addition of an acid, thereby lowering pH, or it can release hydrogen ions if the pH should suddenly rise because there's been a big influx of hydroxide ions. So basically, the magic of a buffer is that it can convert strong acids and strong bases into weak ones. So let's look at an example of how this works. So here we have carbonic acid, and it's a weak acid, and because of this, it can act like a buffer. So we know that carbonic acid will exist not only as an intact molecule, but also as an ion. And let's say that our solution with this buffer in it originally has a pH of 6.5. So what happens when we add a strong acid like hydrochloric acid to this solution? Well, one thing that happens is that the pH is going to change. Perhaps initially it'll go from 6.5 down to 5.5. But this negatively charged bicarbonate ion, it can bind up some of those hydrogen ions. And when it does, it takes those hydrogen ions out of solution. And without some of those hydrogen ions in solution, the pH is no longer 5.5, but maybe more like 6.0. So what just happened? The presence of carbonic acid resisted the acidic effect of hydrochloric acid by binding up some of those hydrogen ions, and it helped maintain the solution's pH a little bit closer to the original value of 6.5. Let's look at another example. So let's look at ammonia as a buffer. Now we know that ammonia, because it's a weak base, is going to exist in water not only as an intact molecule, but also as its ion. And let's say that our pH of this solution is originally 7.5. If we were to add a strong base like sodium hydroxide, this can initially elevate the pH to maybe something like 8.5. But what can happen is that this ammonia ion can release a hydrogen ion and help offset the effect of all these hydroxide ions. And when it does, it's going to create a very neutral compound called water. But more importantly, it's going to remove that hydroxide ion from solution and eliminate its effect on pH. So instead of the pH being a very significant 8.5, maybe it only moves it slightly more alkaline to something like 8.0. Because weak acids and weak bases can exist in solution as an intact molecule as well as an ion, they have the ability to resist pH changes by either binding to additional hydrogen ions or releasing hydrogen ions, depending upon the changes in the environment. And therein lies the magic of a weak acid and a weak base and their ability to act as buffers. Thanks for watching.